Hi everyone, this is the beginning of chapter 11. We're going to have two videos that goes over polyprotic acids and bases. Let's get started. What does polyprotic mean? It means it's a species that has one or more acidic proton. An example of that would be an amino acid. They're polyprotic. Of course, amino acids are the building blocks for proteins, and the acidic part of an amino acid is the carboxylic group, which is the COOH. And the basic part is the amino group, which is the NH2 part. Because an amino group is more basic than the carboxyl group, that acidic proton resides on the nitrogen of the amino group instead of on the oxygen of the carboxyl group. So that's why when it goes to the right, you'll see that there's no proton on that oxygen, but the proton was actually grabbed by the amino group, which became an ammonium group. And their carboxylic acid became a carboxyl group. When this happens, this is called a zwitterion. A zwitterion is a species that has both a positive and a negative charge in the same molecule. At low pHs, both the ammonium group and the carboxyl group are going to be protonated, but if you're at high pHs or basic pHs, neither of them are going to be protonated. So now we kind of know some new terms. We know what a zwitterion is. We've kind of reviewed what amino acids are and what makes them amino acids. The amino part is the NH2 group and the acid part is the COOH. This is a table in your book, it's table 11.1, which shows the acid dissociation constants of all of the amino acids. It's going to be a useful table for us for the next couple of problems that we're going to do. Realize that an amino acid is made up of the carboxylic part, the amino part, and the R group, which is it's called the substituent part. All of the amino acids on this table are shown in their fully protonated form. So for example, the amino acid cysteine has 3 acidic protons. You can see right there, it has pKa for the carboxylic, the pKa for the substituent, which is the second pKa, and the pKa for the ammonium group, which is 10.74. This is what you see in your book. It kind of shows you how the process of them losing each acidic proton. So you start out with H3A+, it has 3 acidic protons. The first one to go is the one from the carboxylic group, and you see that the pKa is 1.7, which is exactly what's said right here, 1.7. That's actually your amino acid. Your amino acid is the molecule that has no net charge, so in essence the zwitterion. The second pKa is 8.36, and of course you can see it's the proton off of the substituent group, and that's designated HA-. And the third pKa is even less acidic. It has a pKa of 10.74, and that's finally the one on the amino group. So cysteine has 3 acidic protons, and it tells you by the pKa value, it tells you which one gets taken off first, second, and third. What about diprotic acids? Well, diprotic acids obviously mean that there only has 2 acidic protons, not 3 or more like polyprotic. And of course, that also means that there's going to be 2 acid dissociation constants, Ka1 and Ka2, where Ka1 is greater than Ka2. Of course, that should tell you also that the pKa1 is less than pKa2. Remember, they're the opposite. So the more acidic proton is the one that has the lowest pKa value and the highest Ka value. And here I'm showing you the acid dissociation reactions. Of course, the Ka1 being H2A going to dissociating into HA- and H+, whereas the Ka2 takes the HA- and dissociates that. The same argument goes for Kbs if you're doing a weak base, right? A base dissociation. So if it's a diprotic base, you're going to start with A2-, you're going to add water, and that's going to become HA- plus OH, and then that HA- is just going to add another proton and become H2A. So these are the very general descriptions of diprotic acid, diprotic base reactions. There's a relationship that we can gather from these Kas and Kbs. And remember, this is all going to be given to you in your constant list, so you don't have to memorize them. You just have to know how to use them. So for diprotic systems, you can take the Ka1 and the Kb2, and that equals Kw. So if you add the Ka1 reaction to the Kb2 reaction, the sum is basically water, which is why Ka1 times Kb2 is equal to Kw. From that knowledge, you can derive all of these different relationships between acid and base equilibrium. And I give it to you for the diprotic systems, and I also give it to you for the triprotic systems. Realize that your book omits the subscript A's for the acids. So instead of saying Ka1, they'll say just K1. But for the bases, they do retain the B. Don't ask me why, it's just for clarity, I assume. But just realize that. And these are the relationships that you will use maybe in some problems. So keep them in mind. Remember, you don't have to memorize them. So let's try to do an example. If I want to find the pH in a diprotic system, how would I do that? So if we consider the amino acid leucine, which is denoted in the blue color here, that's the neutral molecule, which of course has one acidic proton and one negative carboxyl group. So this amino acid can either accept a proton to the carboxyl group or lose a proton from the ammonium group to give L-. So it's the intermediate form. A general statement that I'm going to say is that a solution of diprotic acid behaves like a solution of a monoprotic acid, which should be a relief because we know how to deal with monoprotic acids already. So if I wanted to write the equilibrium constant for this amino acid, HL, I would start with the most protonated form, which would be, of course, H2L+, because it has two acidic protons. So the first one has a pKa of 2.328, and that's the proton on the carboxylic acid. But anyway, if we start with the most protonated form, it would be H2L+, dissociates to HL plus H+, and that's your K1. What would be the second dissociation constant? It would be taking that HL and dissociating that. So it would be L- plus OH, and that's your K2. Now, let's try to set out to find the pHs of these individual solutions, of the H2L+ and then of the HL. Let's first do the acidic form, which is the most protonated form, H2L+. If we have three individual solutions, we have 0.0500 molar of H2L+, 0.0500 molar of HL, and 0.0500 molar of L-. But let's first try to find the pH of that 0.0500 molar H2L+, which is the most protonated form. H2L+ is a weak acid, so this becomes very familiar to us, thank goodness. And HL, you have to realize, is even weaker, okay? And we can determine that by the pKa values or the K values. And that K2 that they got for the HL, you can figure that out if you go to the table and you see that the pKa for the second proton is 9.744. If you put that value negative and raise it to the power of 10, you'll see that you'll get 1.8 times 10 to the negative 10. So it's super, super small because your K1 is 4.7 times 10 to the negative 3 and your K2 is way, way smaller than that. With those two numbers, you can actually make a really cool approximation saying that H2L behaves like a monoprotic acid. Why can you do that? Because you know what the K1 is. It's really small. Let's start to begin with. It's a lot smaller than that 0.0500, which is the formal concentration of that weak acid. But like I said, look at the K2. It's like ginormously smaller than the K1. So really, it doesn't really dissociate at all. So for that reason, you can make that approximation that it kind of just acts like a monoprotic acid. If you do that approximation, it becomes super, super simple because it becomes like everything else we've seen before. To find the pH, you have to find the concentrations of H+, which of course you would use your Ka expression, which is our regular x squared divided by f minus x. You know what your K is because you've got it from your table. And then all you do, you know what your formal concentration is, which is 0.0500. You plug all that in, you solve for x using your quadratic equation, and there you go. You get your x equal to 1.32 times 10 to the negative second molar. That is the concentration of H+. So to find the pH of that, you just take the negative log of that value, and you get 1.88. From that, you can figure out what the concentration of H2L+ is, which of course is f minus x. And that, of course, equals out to 3.68 times 10 to the negative second molar. So that's how you find the acidic form of a diprotic acid. What if I wanted to find the concentration of the L-? Remember, H2O plus was the first dissociation constant. Remember, it went from H2O plus in equilibrium to HL plus H plus. Then we would take that HL and dissociate that. That's the second dissociation constant, which is shown right here. And what if I wanted to find the concentration of L-? All I would do is use my K2. I know that the equilibrium expression is going to be H plus times L- divided by HL. I know that I can solve for L- by just rearranging my terms there, and that would give me K2 times HL over H plus. I figured out what H plus was. I know what HL is. It's the same thing as H plus, and I know what my K2 is because I have it from the table. So I plug all those numbers in, and I can find the concentration of L-, which is 1.8 times 10 to the negative 10th molar. Realize that the approximation that second dissociation constant or dissociation of the diprotic acid is much, much less than the first one. It's confirmed right now. I mean, it's about 8 orders of magnitude smaller than HL, so it really doesn't dissociate at all. Generally speaking, diprotic acids behave like monoprotic acids, meaning that the Ka is going to be equal to K1. So now what about the basic form, L-? So we did the acidic form, which was H2O plus, and we found the pH of the solution, and we also found the concentrations of each individual species. But now what if we wanted to do the L-, the basic form? Well, guess what? Thankfully, the fully basic form of a diprotic acid can be treated as monobasic. Yay for that, because it's exactly what we did before. We can use the same approximation. Obviously, the reaction is the same. You have your protonated leucine, you have your leucine, which is the intermediate form, and then you have your basic form, the L-. So now we're starting from the L- part. And if we're doing the base hydrolysis, we're going to take the L-, we're going to add water, and it's going to be in equilibrium with HL plus OH, and that's your KB1. And how did I find that? You would just take your KW and divide it by your Ka2, and that should give you 5.55 times 10 to the negative 5. And then you do the second hydrolysis, which would be taking your HL and adding water, getting your acidic form back, H2O plus OH, and that's your Kb for that reaction. Notice here that the Kb is quite small. So again, that means that it's the opposite. It won't hydrolyze very, very much. And Kb2 is even smaller. So guess what? We can do that fantastic approximation that we did before, just the opposite. So therefore, we can treat L- as a monobasic species, meaning that Kb is going to be equal to my Kb1. And the results are right there. You can take your x squared, you do your Kb expression, which is x squared f minus x, is equal to your Kb, and then we solve for x using the quadratic equation. We find out that that's 1.64 times 10 to the negative 3. Realize that's the concentration of OH. So to find the concentration of H plus, we just go ahead and use the Kw and divide the concentration of OH, which would give me 6.10 times 10 to the negative 12. Then I find my pH was 11.21. Now to find the concentration of L-, all I do is F minus X, which is 4.84 times 10 to the negative 2nd. And of course, if I wanted to find the concentration of H2O plus here in this basic form solution, all I got to do is find it from the Kb2 equilibrium. So I know here that my Kb2 expression would be H2L plus times OH divided by HL is equal to my Kb2. All I do is I can solve for H2O plus because I know everybody else in there, so that would give me H2O plus is equal to Kb2 times the concentration of HL divided by the concentration of OH minus. I know what the Kb2 is. It's right here, 2.13 times 10 to the negative 12. I know what HL is because that's my X, and I know what my OH is because that's my X, equals 2.13 times 10 to the negative 12. That is the concentration of H2L plus. All right, guys, that does it for this video. I'm going to pick up the second video in the same section, we're just going to go over the intermediate form, which is the actual amino acid, the HL, which is a little bit tougher. And that video is also going to deal with trying to find the principal species in a solution. All right, guys, see you later.